Yeah. So we talked about this Lamborghini thing, which is the high-end expensive items in aerospace and defense. In the high space, the basically high value components. They use composites both in aerospace and also in aerospace and also in what is it called automobile. So composites are not cheap, especially carbon fiber composite, carbon fiber reinforced polymers. The glass fibers are cheap, so you get a lot of cheap composite items also, like chairs, pipes, but these are glass fibers. So glass fibers are reasonably cheap, but the moment you go for carbon fiber or boron, these become extremely expensive. Okay. So that's where we conclude the composites. Now, the idea of this session was trying to identify basically what are the mechanical properties and how do we go ahead and choose those mechanical properties. So primarily what happens is, okay, it's not letting me erase it, but typically weight and expense, these are the two important items of composite, because whatever we design, right, we want to have light designs. So we need to identify properties. The first property is stiffness. Now all of you know that stiffness, if you want to talk about, okay, for some reason it's not working. Okay. So one of the key things is you go with weight. So weight is one of the primary things, and then there is expense, the price. And so these are the general thing. Whenever I use a material for design, I would look at how light it is and how expensive it is. Because if you see, I can buy a computer for, if I want to buy a laptop, I can buy a laptop for 20,000 rupees. And I can buy a high-end laptop, the latest Apple, for a few $1,000s. The difference is in the materials, right? They use a mag alloy. The cheap one will use very cheap plastic. So basically, if I'm designing something, the weight and the expense are true primary criteria when I talk about materials. So that's one of the most important things. Then the mechanical properties is very important. There's something called stiffness. So this stiffness, what do you mean by stiffness? So how do you characterize stiffness? Stiffness basically means if I am applying load, it should not deflect. Now there are two ways to accomplish this stiffness. I either choose a material with very high modulus of elasticity, or B, what I can do is I can make it really fat. So it can be either a material property or geometry. Then one of the other important thing is, okay, so the other important thing is something called yield strength. So when I'm designing material, I don't want my material to fail. In most of the design criterion, I would use, if it's a brittle material, I will use fracture toughness. If it is a ductile material, I'll actually use yield stress. It should not yield, because the moment it has yield, structural integrity has been compromised. So my design criteria always is about yield, about the yield strength. Now, there can be yield strength and there can be tensile strength. So yield strength is where we design, tensile strength is where the failure occurs under tension. And for a lot of these brittle materials, one of the key concept is fracture toughness. So fracture toughness is basically understood as resistance to crack propagation. So how does the crack propagate? So how does the crack propagate is something which is also very important, and that is actually characterized by something called fracture toughness. I'll talk a little bit more about fracture toughness, right? And then of the thermal properties, coefficient of thermal expansion extremely important, and thermal conductivity. These two properties are most important. Now, why is expansion coefficient very important? Is because what happens is if my material has coefficient of high thermal coefficient, coefficient of thermal expansion, what happens is because whenever I heat, right, there would be a temperature gradient, there will be a thermal gradient, right? And if my alpha is very large, then alpha delta T will become the mismatch, the strain mismatch. And the strain mismatch, what it will do is it will create residual stresses, which is undesirable. There will be a lot of residual stresses in the system. So coefficient of thermal expansion should be low. You will get thermal stability, right? It will not deform. There will be no deformation gradient, and there will be no residual stresses. So thermally it will be stable. And the other key aspect is, other thermal coefficient is basically, so I said alpha delta T. Now, so there are two components to strain, epsilon alpha delta T. One is alpha, the other is delta T. Now, my delta T will be large or small depending upon the thermal conductivity. Imagine two situations when I have a large thermal conductivity and I have small thermal conductivity. Now, can somebody tell me? Of course, you can use the chat box to tell me which one will have large delta T. Low thermal conductivity or high thermal conductivity? Anybody can just type in and then I can announce it for the class. Where do you think? So very correct. The low thermal conductivity basically means that, very good answer. All of you are saying low, because low thermal conductivity means there will be heat will be locked, right? The heat will not be diffused. The moment it is not diffused, you will get a localized temperature rise. So there will be local temperature rise, and there would be there will be lower temperature far off from there. So you'll have a high delta T. So this high delta T basically means the thermal strains will be there. Alpha delta T will be there. So this thermal strains can either come from alpha or it can come from delta T. Both can create these thermal strains. So thermal conductivity will actually govern the delta T. Expansion will govern the alpha. In the output is same in both cases, that you will get a large thermal strain mismatch, which is undesirable. So there will be thermal strains in the system, right? Which you don't want in your design, right? And then there is another thing, is electrical conductivity. So if I am designing something where it has to be electrically conductive, I need to identify the properties where the material is electrically conductive. So that's something where we want a thing. And then there is other important thing is corrosion and oxidation. So imagine if I am trying to design a marine application, right? I have to design a pipeline which will go under the sea. What is the key requirement? Can somebody type it out and then I will talk about it? I have to use, I have to put a pipeline inside the sea for some reason, for pumping out the crude from Bombay High or providing something else. But primarily these are, so the primary issue would be, it's a very corrosive atmosphere. Marine salt water has lot of, the sea water has a lot of salt. And this salt can create corrosion, right? So corrosive atmosphere becomes a very big issue. So now, how do we, so basically there are material loss can occur three ways. Physical wear, this is because of contact pressure, corrosion because of chemical wear, and oxidation also is a form of corrosion. If I'm exposing it to an ambient condition, especially say in Mumbai, right? It's a big problem. There's a lot of corrosion because we have a lot of humidity in the air. So it will cause corrosion. So depending upon what application I want, I need to know whether the material has wear resistance, if there's a physical contact between the materials, or corrosion, if it's an application where you want seawater or marine applications, or oxidation if you have open air functionality. So these things have to be accounted for when you talk about your material selection, right? So these are the properties which I talked a little bit about. Now what we'll do is we'll go ahead and so fracture toughness is another very interesting concept. Okay. So fracture toughness typically is actually important to see how the material is crack resistance. So crack resistance basically means is if you have a material where there is an initial crack, of 2C length and you are putting stress. So basically, where does it, at what stress it fails? That stress is called sigma T. That stress is called sigma T. And there is a shape factor beta. You see there is beta sigma T pi C. Let me just delete everything. Just 1 second. Let me do this. I'll use the pointer mode and then maybe able to do. Yeah. So basically there is beta here and then there is sigma T pi C here. So basically what happens is for fracture toughness, you have a pre-created crack of 2C length. And then you basically use stresses of sigma here, sigma T, and it fails at some stress sigma T. This is that sigma T stress. And there is a beta term here. This beta term is because of geometry, because where the crack is located, what is the size of your specimen. So to accommodate for that, you would need beta. And that fracture toughness is very well defined for brittle materials, but it is not very well defined for so basically, fracture toughness is a key property for ceramics and not for metals, because ceramics fail if there is a crack. The crack resistance of ceramics is not very high. So so typically ceramics will fail because of this fracture. Now I wanted to illustrate those mechanical properties. So if everything is all right, your material is stiff. So now you understand what stiffness means, right? So stiffness basically means that your pointer options. Let me just go play that. This is very good. So stiffness basically means that you have modulus of elasticity E. But there is another way to increase the stiffness also. There, what you can do is you can have a thicker section. So either I have higher modulus of elasticity or I have thicker section. So that is the only way to have higher stiffness. Now you can also have strength. So basically strength is sigma y, and strength basically means that there can be some plastic deformation. So here there is in third figure, there is plastic deformation here. And if it is not tough, means there will be fracture. So fracture by definition is all of a sudden, right? I showed you this fracture is a sudden phenomenon, right? Yielding and failure, there would be, it will go and basically go and it will deform for some time and then fail. But then fracture is something that happens immediately. You see, it just catastrophically fails. And then there is something called density, right? If I make parts out of very heavy row, then there will be self-deflection. So there will be self-loading, which will be detrimental to the structure. So you cannot make things out of very heavy materials. So that's a problematic thing which you have to understand, right? So that's the other issue which is there with material. So basically, stiffness, strength, toughness, and density. These are some of the key properties which you would need in material design. And typically, how do you create that data? The way you create that data is first you do a test. From that test, you actually create a test data. So it will be a strength data, a stress strain data. There will be, and then with that test, you'll create design data basically. So with design data, you can create, and then there would be potential application. So after you have designed, then you can select the material and processes. So basically, you'll have to select what material to use and what processing techniques you would use. And then after that, you will have a potential product, right? So these are the steps. And how do you get the material chart? Material chart can be that you can have various materials, and for that various materials, you could figure out what will be the properties. So you can make some sort of a bar chart. This is the simplest way to get material data. So like diamond is the highest elastic limit, right? You all know that diamond has the highest E. The problem with most of the ceramics, if you understand what ceramics are, Ceramics have very high modulus of elasticity, and they have very high something called compressive strength. So they're very strong under compression. But the moment you start doing tension, these things are not that good for tension. So compression, they are very good. They will have very high both E and sigma Y, but the moment you put it in tension, the crack propagation can take place because inherently these are made by a process called sintering. So these are powder by nature, and this powder you have basically provided some bonding agent and fired it to create a solid piece for you. Okay. So that is there. And then thermal conductivity, if you see, is another. So basically, you can look at the properties for this thing. Metals are also reasonably strong. Ceramic is the strongest of all, of course. Diamond being the strongest material known to man. And then you would see tungsten is exceptionally strong. So the strongest metal which is known to man is tungsten. So you can use tungsten in case of high strength materials. Then there is something called, you have polymers. Polymers have different applications. Typically, they do not have very high strength, but they can take a lot of impact. The moment there is a need where you have to absorb energy, polymers are the right material to do it. And then if you want to know, you can also have composites. Composites can have phenomenal strength because it's a function of what kind of reinforcing material you use. If you use carbon fiber, it is very strong. And if you use, so there are modern things also, which are like carbon nanotubes. So carbon nanotubes can be super strong. So you can make composites with very strong properties. But the problem with composite making is expensive. So you'll have to have you need to have the processing technique right. So composite is not easy to process. But then composites have a lot of advantages. They have very high toughness. They can take a lot of energy, and they can also have engineered strength in any direction you want. So if my loading is somewhere, so I can actually create large strength in the direction of loading, which is not there in any other process. It's not easy to do that in any other process. So that's the thing. And then you can also have properties regarding like thermal conductivity. Now, thermal conductivity, if you see, typically these ceramics have low thermal conductivity, which basically means they lock the heat. And metals are typically things with high thermal conductivity. Although diamond is a reasonably good thermal conductor, but most of the ceramics, if you would see, they're very low thermal conductivity. And polymers, of course, also have low thermal conductivity. So whenever you have to conduct the heat, so imagine if I have to make a fin, I will use a material which has very high thermal conductivity. And so these are some of the examples of property charts. Now, how can you use structure toughness? It is not energy related. That's his question, right?
Yes.
Let me just go ahead and read it, and then I'll. Okay. It's not energy limit. It's fracture toughness is something which actually is very catastrophic, right? Because what happens is some materials have a different way of crack propagation. So what happens is, if there is a crack, this material will fail immediately. So it is not like your metallic thing, right? Where you have gradual failure. So there is large deformation, large plastic deformation. So fracture toughness typically is used in design where you want to measure the crack resistance. So typically what happens is, how does failure occur, right? Typically what happens is failure can occur in two modes, right? The first one is I keep on deforming the material yields and finally fractures, right? That's one way material can fail. In a lot of cases, what I do is when I do cyclic loading, right? When I do cyclic loading, what may happen is, in cyclic loading, there can be small crack which is there in the system, some discontinuity in the material. It starts to propagate, and after a while, what happens is the crack is so large that the material can fail catastrophically at one go. So it's not an energy parameter. It is measured for, and this is more critical in ceramics. So what if you see this thing, right? Failure is almost 10. So you're pulling the material is nice and linear, and all of a sudden, boom, the material fails. Right? And there will exist a value of sigma t for every 2c. If 2c is larger, sigma t will be smaller. You get me? So this is for catastrophic measurement. This fracture toughness is not an energy measurement. It's not the measurement of the area between stress and strain. Right? So let me do this. I think I've gotten my computer back up, the other one. This should now work. Looks pretty smooth to me now. Okay.
Hello, sir. Sir, you are muted again. I just had a question, sir.
Yeah.
Yeah. Here, what exactly is beta? What value can it take, and what does it depend on exactly in the geometry?
So beta, I'll tell you, beta, what is happening is beta depends upon where the location of crack is. Right? This crack can be in the center. This crack can be towards the edge. Right? If the crack is towards the edge, it is more critical. So you have a correction factor here in terms of beta. So imagine my crack is not in the center, it's towards the edge, right? It will fail much faster, right? So that is where beta is there. Beta is a factor which actually tells the geometry and the location of the crack. Is the crack in this direction? So basically, crack, you need a correction factor of the location of the crack. This is the correction factor for location of the crack and geometry of the crack. I'll teach all that. Okay.
Okay, thank you, sir.
Yeah, so that you don't have to worry about. Okay. So this is one thing. So this you understand now. This also you understand how do you get data from test data. How you create data, then you have design data, then you have potential applications, and then you have real app. So basically you do tension test, compression test, torsion test, get that data, get a statistical map, because what happens is there is a variation in the test data. If I test same thing, I'll get some variation in the property. So I need to get the statistical analysis done to categorize the material property and then identify the material property. Once you have design data, I identify what kind of materials I will use for that application and then create something called bill of materials. Right? And with that bill of materials, I'll go ahead and do my fabrication and manufacturing. Right? So basically, one of the key things which I want to show you is something called stiffness to weight ratios. So the stiffness to weight ratios are basically is very important, because when I'm doing an application, right, I want my structure or my component to be very stiff but very light, right? Because if I'm designing a plane, right, I'm using composite, I'm using aluminum. Say the first class of planes, right, they use steels, but they figured out that steel is useless. So can somebody tell me why would they stop using steels in planes? What was the thought process? So what does weight do? Of course, it is heavy, right? Why would I? So if initially the first few planes which were made, they all were made of steels. And then people realized, okay, steel may not be the best thing to use. People started using aluminum. So weight was a big constraint, right? The heavier the plane is, the more thrust you need to lift the plane up, right? You need more thrust, you need stronger engines, and it's it's very expensive, because if you are hovering around, so Mumbai, people, you have landed in Mumbai many times, right? Typically Mumbai is very crowded and you have to probably hover around in Mumbai sky for 15-20 minutes. So every half an hour the fuel cost which you lose is roughly 60 to 80,000 rupees. For every half hour they hover around in the plane, they lose 60 to 80,000 rupees, which is a significant portion of their earnings. So imagine how critical it is to have low weight. So that's why most of the new planes, people are going through composites. Our Tejas also, our new fighter plane is all composite. The wing is composite, the fuselage is composite. So composites make sense because they are very light and they're strong. So you don't compromise on strength. So this is where we talk about. They're stiff and they have low weight. So let me just show you some of the charts which I have. So there is this chart is called, this chart is basically modulus to density. So this is a very important chart. I'll actually show you something. How do you use this chart? So basically, see which material has highest modulus. If you see, the usual suspects are ceramics, because ceramics have very high modulus. They have very high strength also, but right now we're talking about modulus, so they have reasonably high modulus. So diamond has the highest modulus, if you would see. And these are also tungsten carbide, and cobalt also is a kind of ceramic, although it behaves like metals because it has high thermal conductivity, and it has some metallic properties. Typically, ceramics are insulators. So basically, this is called hard metals, but it is also kind of a ceramic only. Tungsten carbide, cobalt, these are tool materials, cutting tool materials. Diamond, silicon carbide, silicon nitride, zirconia, these are super hard materials. They have high strength as well as high modulus. So if you see, and they have low density. So if you see E by rho, they have very high E and reasonably low rho. And again, if you see polymers have very low density because they're very light, but then they don't have super high elastic modulus also. But then you just look at the ceramics. These are the ceramic ones. I'm showing the ceramic ones. See, ceramics all of a sudden have very, very high modulus. The reason why high modulus is, I showed you that, right? I showed you how the modulus changes, right? My E, if I put a very high modulus fiber or the hardening phase in it, the strengthening phase in it, you will get high E's. So you see reasonable amount of stiffness and very light material. So if I have to use high modulus to density, I'll either go with ceramic or I will go with composite. Now I have a question. Where should I go for ceramic? Can I make a plane out of ceramic? It has very nice thing, but can I make a plane out of ceramic? If not, why not? That's my question. Can somebody answer it? I just want to see how you guys answer this question, because I need high E by rho, right? I'm going with aluminum. I'm going with titanium alloys, aluminum alloys, which have high E over rho. So brittle is one of the issues. I cannot make free from ceramic. Yes. So all three are right. It is brittle. Crack propagation is very easy. I will not have any fatigue life. That also is a very good answer. I cannot take any fatigue life. It cannot take any cyclic loading. That's a very good answer. Now the question is, even though it has the desired E by B rho ratio, I cannot use it. It's not machinable. It cannot take fatigue loading. It is very brittle. So I'll have to take this call that not the desirable properties, along with certain other things which are required, are also important. So they have very desirable E over rho ratio, but at the same time, it cannot be manufactured easily. It can create problems with cyclic loading. But at the same time, a lot of these engine components, which people want to make, silicon carbide, so very high temperature engine components, people are moving to ceramics actually. So engine components, people are trying to make ceramic. A, it will be lighter. B, you can go to temperatures which are unimaginable with metals. So silicon carbide composites, if I can make it reliably, if I can make sure that it doesn't crack, right? If it has a reasonably good amount of fatigue life, I will actually make super high temperature engines. So people are trying to look at that. So that's what I'm trying to say, that if I can address some of the issues, I should be able to use it. Okay. So modulus density is one of the things. Okay. And then same thing I can do with strength to density. I can do strength to density, right? So strength to density, if I see this engineering alloys, if you see these engineering alloys are there, and so these engineering alloys have very high strength to weight ratios. But again, if you see ceramics are again, let me just go back to this.
So
Yeah.
So no, I was just saying, could you make the screen big?
Yeah, that's what I'm trying to do. Actually, I would have loved to annotate it and show you some of the things, but unfortunately, I don't know what happened. Where did it all go wrong? I had kept everything annotated, everything ready for it, but some reason. Okay. Shoot. Okay. Right. So basically, if you see strength to density, let me just go ahead and use the pointer option here. Yeah. So this is ceramic. On ceramic, all the strength to density ratios are best. But again, the issue would be they have very high compressive strength. So ceramic, we are reporting compressive strength, ceramics and glasses, and they have reasonably high compressive strength. But tensile strength is much lower. It's still reasonably high, but it's not as compared to the compressive strength. Compressive strength is very, very high. They actually show some degree of asymmetry in the strength, in the compressive and tensile strength. Okay, and these are the engineering alloys, if you see. So titanium alloys are right here, very high strength and very well load. Steels, if you see, they have reasonable amount of weight, and although the strength is there, but if I am conscious of weight, I would go with these. So this is what we talked about.
So there is a question in the chat.
Yeah, what is it?
Question is, how are carbon fiber sheets made?
Okay.
Is it also as high strength bitter material?
So that's a very good question. So what they do, there are multiple ways of making carbon fibers. One is something called pre-preg. So pre-preg basically means that they will take the fiber, either woven or laminated. Laminated basically means they will have a direction, 0 degree, 90 degree, 45 degree. We can make plies and assemble the plies up. So what pre-preg basically means is that you have some resin which is pre-embedded in it. So fiber is just not like that. You're not laying up fibers every time. That fiber is actually infused, pre-infused in a polymer. Now, the reason why this is actually good, if you would like, the reason why this is good is because it has a polymer matrix. So this polymer matrix, what it does is, it actually, sorry. So the polymer matrix, what it does, it actually gives us some degree of it's not brittle. It gives some degree of ductility. Or ductility, more than ductility, it gives us some impact strength. So it can be deformed. So that's what happens with this thing. And this pre-preg, what you do is this pre-preg you can lay out. So either you can do a hand layup with the mold, or you can do something called the tape laying, which you saw. So the modern day thing is people do tape laying. Tape laying is the new thing which people do every time. Okay, so modulus density I talked about, and then I talked about strength to density. So you see metals here. These are titanium alloys, which are and steels are somewhere here. If you see, steels are somewhere here. So if I want light, I would use titanium. And composites are very good. So composites, this is what you see. Composite have basically, it is, so ceramics are right here. Ceramics are right here. Again, ceramics have a very high strength to density ratio also. But the problem is that they tend to fail catastrophically, and manufacturing is a nightmare. So now what happens is, and then they don't have any, so they will fail in something like this. I load, they fail immediately right here. Composites are very attractive because composites have polymers. Polymers inherently have reasonable amount of ductility and high impact strength. So composite is a very attractive thing. If I want high strength to density ratio, if you see, so basically I have this E by rho is equal to 1. This line is there, right? Anything with this slope has very high E over rho. This slope has E over rho ratio. So now if I see this, right? Now design guidelines are there. If you see, let me just go back here. You see there are design guidelines for E over rho here. So this one is E over rho is equal to constant. This one is E 1 by 2 rho is equal to constant. This is E 1 by 3 rho is equal to constant. You know why they use something like this? These designs which they have given. Why would they use these E over rho, E 1 by 2 over rho, E 1 by 3 over rho? Why would they use that? So if there is a pure, if I am using E by rho for uniaxial, I just show you. For uniaxial condition, E by rho, you will use E by rho. But if I have a beam bending, if I have a beam problem, I will not use E over rho, but I will use E 1 by 3 over rho. I'll show all this. I'll actually show these calculations right now. And for panel, it is if I have a panel bending, if I have a 2D bending problem, then I will use E 1 by 2 rho. If I have a beam bending problem, I use E 1 by 3 rho. I'll actually solve these problems for you. But today what I'll do is I'll show you a very simple calculation. So imagine I have to engineer something which is something like a simple tie rod. Everybody knows what a tie rod is, right? So tie rod is something that just takes tension. So imagine I have to tighten something, right? A tie rod can be if I have to tighten a flange, say. If there are two flanges, right? Two flanges. If you have, say, two flange, everybody know what a flange is, right? Who doesn't know what a, so those who don't know flanges, I'll tell you what a flange is, and then I'll start from there. Everybody knows what a flange is? Anybody who says no, let me just go ahead and explain that. So a flange is, so flange basically is, so if you have to keep on tightening the flange, right, you will use something similar to even a simple stud. Even if a simple,
We can't see the screen.
Pardon? Can you see it now?
No, sir.
Oh, size you cannot see. Still shared in. Can you see it now? For some reason, yeah. So you see what a flange is now, right?
Yes, sir. Now we can see.
Okay. So this is something like a flange. Now you have to tighten this flange, right? So you need some sort of a stud. Stud is a bolt without a head, right? So I will use that stud and tighten it on both sides. So this will be, so that member is under tension. So I'm designing a tie rod. A tie rod, typically what it does is it is in tension and it is supposed to take some force, right? So that is what a tie rod means, is that tie rod is in tension and it is engineered to take certain critical force, tensile force, say F star. Now I want to design this tie rod. So basically I know my function, let me just go ahead and make this like this. So my function here is that it is a tie rod. Now I'm designing this. Let's say I want to design this with minimum mass. I want to design it very light. This is aerospace grade tie rod, right? I'm tying something in where weight is the primary concern. So I have to minimize the mass. Imagine this is a tie rod for aerospace application. I'm tightening I'm using it in some very critical application. Now the constraint which will be there on design will be I have to have a length. This is by design. This length is required, and it is supposed to take f star. So these are constraints, right? And design objective. So any designing, right? Any optimization problem has something called objective function. Second thing is it has constraints, and of course function, you know. So objective function is minimize m. Constraints are that L is fixed and it has to take f star load, right? So now if I start to do something like this, I know my sigma yield of this material, whatever material I choose, right? Now I have to choose my material. So my free variables, if I want to say, my free variables will be A, area, and the material, right? These are free variables which I have to identify here. So sigma y, so sigma y is equal to should be greater than or equal to f star over A, right? This is something which you know, f star over A, right? Now my m is equal to rho times L times cross sectional area, right? This is my rho into volume, which is rho LA. Now my A is what? My A is m by rho L, right? If I plug in here, what will I get? Sigma y is equal to f star, or not is equal to, let there be inequality here. F star over 1 over A. 1 over A is what? Rho L by M, right? So my M should be greater than or equal to F star rho by sigma y, right, times L. So you see this rho by, so if I have to make M lowest value of M, rho by sigma y should be minimum, or sigma by rho should be maximum, right? Let me just go back here. So this is what I want. So there is a functional constraint, which is f star, which I showed you. This is what the load it should take. This is geometric constraint, the length, and then there is a material property. So M should always be greater than or equal to f star, which is a functional constraint. This is what function it's supposed to take. And length is again a geometric constraint. And this is where I have to choose rho over sigma f or rho over sigma y, let's say. If it is yielding condition, rho over sigma y should be minimum, right? Then only my mass will be minimum. So what I can do is I can say sigma y by rho should be maximum. And for stiffest tie, it will be E over rho for uniaxial loading, right? So now what I do is, if I have to do sigma y by rho, I go back and see. Let's go back to sigma by rho. This is the chart, right? Sigma by rho. If I have to choose, what material will you recommend? Just type in your chat boxes. What material do you think we should recommend? Look at this. So I know I have a uniaxial thing. So sigma by rho is equal to constant. So this is the one which I should worry about. So this is the sigma by rho. I keep on going parallel and choose the material. So a family of material will have same. Yes. So this is you still see the screen, right? The screen is visible,
Yes,
right?
Yes.
So this is E by rho line, right? This is the E by rho line. Now anything parallel to E by rho would have same strength, same strength to stiffness ratio, same strength to density ratio, right? So anything I choose has same E over rho. So now you have to take a judgment call. Which material to choose? So how will you take the judgment call? How will you take the judgment call? What material to choose? I know I'm designing this material. What will I choose now? Based on this, whatever we have studied up till now, what would you recommend for tie rod? You have this chart here, strength to density chart, and this is the E by rho ratio, constant E by rho ratio. So anything parallel to this will have same E over rho ratio. So how would you go ahead and choose the right E over rho ratios? Let me just go ahead and see what you guys have to say. Most left material. What does most left material mean? Read out the left material. What is that material? So just give me some examples. What will you choose for this condition where you have to maximize E over rho? What will be your material of choice?
They have responded as composites.
Yeah, I saw composite. So composite is there, but composite typically what happens is it still deforms, right? Composite under tension, it will have some deformity. Composite is a very good answer. So ideally you have only two choices. Either composites or we go with metals. Tension will not use ceramics. Ceramics is not a very right material for any tensile application. So you only have two valid choices. First one is metals and composites. Both are reasonably good answers. But you will go with metals primarily because metals will also have reasonably high E, and it doesn't deform that easily. Composite can take a lot of tension, but there will be some deformation. Your modulus of composite can be close, but then you'll have to pay a lot more money. You can get some composites to serve the purpose, but metals will be much cheaper and you'll get similar E over A ratios. So for this, unless and until you have something where composite price is validated, you'll go with metals. So you have two choices here, composites and metals, and you will choose metals for this kind of an application, right? So this is one aspect which I showed you. And then what I will do is I'll quickly go over all the other things. And then we can have so now fracture toughness and modulus. So fracture toughness and modulus, you see the problem comes is the ceramics are in very bad shape. These two are ceramics, very bad shape. So if fracture toughness is a criteria, fracture toughness to modulus is a criteria, I have very low fracture toughness for ceramics. So wherever I have issues with fracture, I will go with metals and engineering polymers. So polymers and metals will be my choice. Ceramic will be a no in this condition. Now fracture toughness to strength. Again, ceramics are not a good fit. So wherever fracture toughness is concerned, I will not choose ceramics, right? I will go with metals. And in some cases, composites are also there. So if you see composites are engineering, if you see composites are somewhere here, composites somewhere here, but metals outperform composites. So fracture toughness, metals are the most superior. They will outperform. So if it is something where you want you don't want sudden failure, metals will be a right thing for the most part. They are more tolerant to cracks. But composite is also a good choice. There's a lot of overlap between composite and metals in this case. And polymers are right here. With they have lower than they're better than most of ceramics, but lower than metals and composites. Now, one of the other very good things is something called thermal conductivity and diffusivity, right? So thermal conductivity and diffusivity primarily. So diffusivity is sorry, let me just go back. Let me just go back. So diffusivity alpha is equal to K over rho C. So typically it should be linear because alpha is proportional to here. Oh, actually they have used lambda here. Let me just do this. So basically diffusivity is, they have used A here because alpha they have used for thermal expansion coefficient. So A is equal to lambda over rho C. C is the specific heat. Rho is density. So ideally A should be A and lambda should be proportional. But what happens is, because there is rho in the denominator, so you should get a line. Whatever is A, you should get. But ceramics, you see, since the density is low, ceramics have this lambda over diffusivity very high, right? Because they have low thermal conductivity, but they have also low density. So ideally, what happens is you should be able to say ceramics. If you see, oh sorry, it's wrong. These are actually metals. I should take that back. So these are ceramics right here. These are ceramics here, and metals are These are metals actually. These are metals. Okay. So metals will have very high thermal conductivity. Copper alloys are on the top, and ceramics have low thermal conductivity, but diffusivity is reasonably high because they have low rho, right? So that's why ceramics also line up pretty well here. And then there is another very important concept is coefficient of thermal expansion and thermal conductivity. This is a very important concept. You have alpha, which is thermal conductivity, and alpha, which is coefficient of thermal expansion, and lambda, which is thermal conductivity. Now what happens here is, if there is low thermal conductivity, which basically means so this is basically alpha delta T is your strain, your thermal strain. Thermal strain is alpha delta T. Now what happens is, the moment I have low diffusivity, I have low thermal conductivity or low diffusivity. So if my K is low, if I am somewhere here, this is low lambda or K. So low thermal conductivity if I have, then this basically means my delta T will be very, very high. This delta T will be very, very high. So delta T is very high because there is localized heating. The whatever heat is being produced is not being diffused. It's still locked there, right? So delta T will be very high. And if I have a high alpha, then meaning that my alpha delta T, there will be a large strain here, thermal strain here. So if I use low lambda, high alpha, it is a very bad combination because there will be large thermal strain match. But if I use low alpha and high K, I will have a small thermal mismatch. So I want to be here. This is my operating regime. If I want thermal stability, in my system, I will use low alpha, and I will also use high lambda, high thermal conductivity or high diffusivity. Make sense? So this will be expansion of thermal conductivity concept. Okay. Now expansion to modulus, if you see, again, my coefficient of thermal expansion to modulus, I have very high modulus, low thermal. Ceramics are very thermally stable. So if I want to make an insulator, I will use this. I want to make a scale. So glass scale is actually very precise. Most of the precise measurement system, positioning system uses glass scale. Or there is a metal called it will be here. It will be written here. I'll just read it out for you. It's starts from magnesium alloy. So it has coefficient thermal expansion is extremely low of that metal. It is called I'll have to look at it. It starts with I. Somehow I'm just missing it right now. It starts with an I. It's not. So the material which was made with the actual meter standard, right, which got decommissioned now in Paris, the ISO standard of meter was made of that material. And if you want really, it has very low coefficient thermal expansion. Very difficult to machine though. I just slipped out of mind. I'll let you know when when it occurs to me.
So is it Invar?
It's Invar. Correct. Thank you very much. Invar. Yes. Thank you very much for reminding me. So normalized strength to expansion, if you see. Now, strength to expansion, you see all of a sudden you have a very different beast here. You have high elastomers and polymers, which are most preferred. Polymers and elastomers. So if you want high strength to expansion ratio, then you have to use. So if you want somewhere you want a lot of thermal expansion, expansion as in like lot of linear expansion, right? It's not just thermal, but it's also it can be thermal expansion also, but it has very good thermal shock resistance. So if I take elastomers, right, I will have reasonably high E over alpha ratio, right? So these are, here you see elastomers and even polymers behave better than ceramics, because most of the metals and ceramics they do not deform as much. So thermal shock resistance also, if you want to see shock resistance, polymers will have both thermal and mechanical shock resistance. Both they have better thermal and mechanical shock resistance. Of course, the problem is that these do not. You cannot use it beyond a temperature. So you will have to identify the right materials to use. But if you see all the gaskets, if you see, right, pressure cooker gasket, these are all elastomers. So you'll have to use some of the materials which can withstand high temperature. So some of the O-ring materials have very high temperature standing capability. In some cases, Teflon is there. That also has reasonably high temperature. But there are certain polymers and elastomers which can actually take high temperatures. But most of them cannot. Most of them cannot go beyond 200 to 300 degrees centigrade. So now strength at high temperature. So here strength at high temperatures, if you see, ceramics and nickel superalloys. These are the material of choice. So I think that the time is over. So I'll stop here. And then what we can do is we can have a 5 minutes Q&A session before we disperse. Okay. We can discuss some questions.
So where are these charts available? Like, are they made for all? So you're muted, I think.
So you're on mute.
Sir, you are on mute, sir.
I get mute all the time. I just don't understand. I think we'll have to figure out, Chaitanya, how to make these guys attendees now. So all of them are like now have the same privileges as us. Okay. So next class, we better figure it out how to take care of this. Okay. So yeah, so go ahead and ask questions, whatever you may have for a few minutes, and then we can disperse. I know you may have other classes as well. Sorry about all the fiasco today, what happened. I'll have to get to a more robust way of doing this. Any questions you folks have? You can type it out in the chat, or whichever way you want to communicate is fine by me. Any questions today? What we discussed?
Sir, in the tie rod problem.
Okay. I lost you, so just type it out and then I'll read it for the class.
Amay, somebody muted you. Can you repeat the question?
I think he somebody probably muted him or whatever. I think we just lost him. You can just put it in the chat box and then we'll take it from there. So there is one question which somebody has asked Srijan Bansal, saying that if F is very low in the problem, can we use other material? Can we use can we use plastic? So what will be the answer? Can we use plastic? Some people say we can use plastics. What is the problem with plastics? Let's say we don't use metal, we don't use composites. Let's say it is in the limits, the sigma y. So my if I do my sigma y over rho, I have a sigma y requirement which can be taken by polymers. Let's say that. Can I use a polymer? Can I use a plastic? How many people say yes? At least I would need some answers.
Sir, our objective won't get satisfied then.
Why not? His argument is F is very low.
F is very low, then we like if we use metals, then our mass will be minimum, and if we use polymers, then our mass won't.
No. If F is very low, your mass will be minimum, right? Polymer is low density.
If we go by the graph, we can locate that E by rho of some metals are less than.
Okay. So let's say I have a polymer which is reasonably light and reasonably strong. Let's say that I have a polymer like that. Will still be polymer be a suitable thing? Let's say we have the required strength. I'll just tell you, polymers, the biggest problem with polymers is they exhibit creep. So if you have a constant tension with the polymer, it will start to become loose. So even though it has sigma y, it's not a suitable thing to use. Composites won't show this creep because it has the enforcing agent in there, which is very stable. And they use thermosets, and thermosets are very, very stable. They
So you are on mute again.
Okay. Any other questions you guys have? And then if not, we'll disperse. But I would like to answer a few questions before I leave. Okay. So what creep is? Somebody asking what creep is. So creep basically means that if I keep a constant load. So imagine I take a plastic wire and hang a fixed load to it. Let's take two wires, one made of metal, one made of polymer. Now, once we take a metal and put a weight in it, the metal will deflect because of the stress which you apply because of the load, and it will show some strain. The polymer will also do it, but the polymer, what it will do is it will keep on changing with time. The metal will not change with time. So if for 2 days later, if I keep this 2 days later, there will be some extension in the polymer, because polymer is a creep basically means at same stress, there will be strain with time, increase of strain with time. So it's a time dependent strain without change in load. So polymers exhibit something like that. The metals don't. Metals only do it at very high temperatures. If the temperature is very high, metal will also show creep, but not at normal room temperatures, no. So that's what creep means. Creep means the change in strain as a function of time without changing the stress. Okay. Any other questions you guys have? Any other things which you would like to talk about, or you have some things which you want to discuss? If not, I think I'm already over the class time. So you folks are free to go. And then if you have any questions, you can just shoot me an email or post it, and then I'll be happy to answer it for you. Okay, and next class I will try not to use PowerPoint. I will actually use PDFs. Sorry about all the problems. I checked it. It was very stable. I did all the annotations. For some reason during the class it started acting up. I'm sorry about that. Okay. So next time I'll actually use PDF. I think that's far more stable and better. Okay. So thank you, and we'll see you in the next class on Thursday. If you have any questions, I'll still be happy to answer them. If not, you're free to go.